Hey, welcome to the next part of the journey with vectors and looking at geometry with vectors. And we're going to talk about planes, and here's the question. Planes, what are they and how would you describe them down here? Hey, something's gone wrong here. These dudes came in. No, I don't think so. They're a different sort of plane, mate. But that plane's going into space here by the looks of things. But we want these flat surfaces. So planes are flat surfaces, and here's some all lined up with the axes. You might just have a look at these axes, these two examples, these screen clippings. What do you notice? What do you notice about those? That's not usually the way that we describe the 3D system. It's usually like this, but it doesn't matter. You could just rotate it around a little and have it in a different orientation like that. So that's what we're going to be doing, looking at these flat surfaces in space and seeing what defines them, how we would describe them, maybe how to find where they cut the axes, or maybe where a line going through would intersect the particular plane. So it's furthering this geometry stuff. And let's have a look now at what these planes are about. Come on down, and what would its equation look like? Okay, obviously, if you're going to find things intersecting in space, the basic idea is to have an equation, or what's an equation anyway? It's a rule that the points must obey to be on that surface this time. A rule for the points to obey. Okay, so that's the idea. And can we find a rule for this point, maybe M, X, Y, Z, that lies on a plane? Oh, what's this doing here? Normal, we've done a bit of those. Perpendicular to a surface is a normal. And that's got something to do with the cross product, hasn't it? So we can find a normal to a plane if we had two vectors in the plane, or maybe 3 points to define the plane pretty well, wouldn't it? 2 points won't, because 2 points does not describe a flat surface. You've got to have a third point. But anyway, getting back to this, there's a general point on the plane, and let's say this is a known point. So can you get some idea, given that we can easily find the normal to the plane using a cross product of two vectors in the plane, could you somehow combine that idea and maybe this general vector from a known point to a general point? Could you combine that and get some sort of little proof? Think about that, because as a budding young mathematician, you should be starting to get excited about what you can do off your own bat there without looking at examples. All right, come down, let's have a look. I've given you the hint now. So here it is. Screen clippings here from Hayes and Harris Publications. So have a look at their book there. And there's our little diagram, and of course here's the crucial step. The normal dotted with this general vector. Remember, I'm saying it's a general vector because I'm trying to describe or find a rule for that general point X, Y, Z on that flat surface, defined by the flat surfaces, defined by the normal to it. Okay, so it would be the dot product is 0 because the n vector is normal to the plane, and this line is a general vector in the plane. And if we dot all that out, so we know the normal and we know the point on the plane, and this is the general point whose coordinates we're trying to describe. So it's A by X take X1, B by Y take Y1, C by Z take Z1. Okay, so here you go. Are you sure about this vector Fm? Let's just take it. F to M, first minus second. Okay, like that. Okay, well, second minus first actually there. Okay, so if you then expanded all this, and we haven't shown this here, and put all the known values on the right, these would be known, wouldn't they? We know the components here of the normal vector, and we know these values of the known point. So we have a nice little rule, okay, of the normal x component by x plus the normal y component by y, normal z component by z equals some number which we could get this number by subbing in x1, y1 and z1 into that side there and get that magic number which defines the plane. All right, so let's have a look at doing one in a minute here and see what we can come up with. This is another form of the same thing, and I want to ask you the question, where did this come from? N dot M take F. Okay, stop and pause the presentation for a bit now and see if you can work out. These are all vectors, they're all in bold here. Okay, I think we know what N is, but what about the other two? Can you work it out? All right, I'm going to show you the answer now. So this is actually from the origin, wherever the origin is, and we're going to take a vector out there, position vector of the point. We're going to call M. We're going to call this one F. Okay, so M take F, what is that? M take F. Well, it's this one here, isn't it? M take F. Sum of vectors around a closed figure is a proof for that. Remember, M take F is from F to M, right? Going backwards there. And just check it by the sum of vectors around that closed figure. F plus M take F take M is back to the origin 0 vector. Okay, so that's the idea, that last side is another way of saying FM. FM there. All right, so you might see that notation. Okay, let's get on with it now. We generally wouldn't use this one because we wouldn't have the position vectors from O. We'd have to work those out and then take them away. It's easier to actually just do FM in that way, a known point to the general point. So here we have the result. If a plane has a normal vector, this, so I have to use a cross product of two vectors in the plane, and passes through a known point, then there's its equation, where D is a constant. Okay, let's do one and see what you think. Find the equation of a plane with a normal vector that and containing the point that. So the normal is that, and this lies on the plane, so the general point is x, y, z. General point to here is x take -1, x plus 1, y take 2, z take 4. So you could do that. You could do the whole thing again. That dotted with x plus 1, y take 2, z take 4 equals 0. If you're asked to show that, that was the normal. But the upshot of that is this. It's 1x from there, 2y, 3z, and then sub this point in. Okay, so you don't need to do this derivation over here unless it's a show that. You want to conclusively show why it's the equation of the plane. Okay, so otherwise you can just then sub these values in, there, and get that magic number 15. Okay, so get the difference between those two approaches. If you just ask for this, the equation of the plane, then you can do it that quick way, and otherwise this is for any question where it says show that. All right, are you ready? Let's have a go. Here's the first few little questions there, question 1 to 3. I want you to try to do this 3-part A in a simpler way without going through that process. The XOZ plane, let's just make sure you've got this. This was drawn on the first page, but here we go. The XOZ plane is the plane through here. Okay, so you might like to think of, and it keeps going, of course, oops, up that way and this way. Okay, you might try to think of a simpler way of getting a rule that all points on the XOZ plane obey. Think simply and then check it with our standard procedure that we've just got there. Okay, pause the presentation, have a go. I'm going to show you the answers now. Okay, so here we go. Question 1, mostly there. I'll show you the bottom of D in a minute. Okay, and question 2 and 3. Okay, so have a look at that and make sure you can see it. Here's the answer I was asking you to look at. You could have worked out without this process that the rule that all points obey on the XOZ plane is that there's no Y movement, so Y is naught is sufficient to describe all points on the XOZ plane. All right, what I want to do now is keep going and develop this a little bit, because we're doing all aspects of geometry with vectors here now. So we've got 3 points. That would define a flat surface. All right, 2 points won't. When you put in the third, you've created a flat surface there. And so if we can find the normal to it, so what are we going to do? Use 2 vectors, A, B, and cross it with AC to get a normal vector. Okay, so remember, it's the determinant of these 2x2 cofactor matrices. And again, I'm suggesting to you, you might write it as a determinant of this 3x3, 4, neg 1, 1, 2, neg 2, 3, so that you get those cofactor matrices correct there. All right, so then when you do this, let's do it. It's AD, that's neg 3, take neg 2 by 1, which is plus 2, which is neg 1, and so on. 2, take 12, neg 10. Neg 8, take neg 2 or plus 2, which is neg 6. Okay, just remember the determinants in here of those 2x2s. Right, so you have the normal vector, and therefore you're going to use these as the coefficients. So it's neg 1 by x plus 10 by y plus 6 by z. Okay, and then subbing in the point on the plane, which is, so that was here, that is actually wrong, isn't it? It should be, so here it's neg 1 by 1, 10, oh no, which one are they using? This one. Neg 1 by neg 1. I think we've got an error there, haven't we? Let's just check this. Neg 1 is, oh no, they've taken the neg out the front. That's okay. They've taken the neg out front. I missed that. So this is 1, 10, 6. And then when you sub it in, we don't need the negative. That just means it would be going in the opposite direction. So we've got 1, 10, 6, and subbing in here neg 1, 2, 0 to get that magic number on the right. So just watch that. Yes, I didn't see that they've taken out the negative there. So it doesn't matter about the negative, does it? Because it's going to be either that way up or that way down, up, and it's going to give you the same dot product as 0. So it's neater without the negative. Okay, and then you can check that these other points, subbing it in here and subbing it in, follow that rule and that you haven't made a mistake. Okay, always worthwhile. Well, let's see if you can do one. So here, the idea, of course, is you've got to find the dot product, the scalar product first, sorry, and using A, B and BC, or any 2 vectors in the plane there. You can use AB, AC, BC, if you like, any of them, to get that perpendicular or normal, which is the cross product. Okay, pause the presentation, have a go, and I'll show you the answers now. So here they are. For A and B, and let's just bring up C, and we'll go on and have a look at 5. All right, so what do you think there? Okay, let's go on and see what more we can do now we've got this equation of the plane. And of course, one thing that I mentioned in the introduction is what you might like to do is to find where a line meets the plane. So we have a line defined by 2 points and meeting the plane. So the first thing to do is to work out AB, the vector AB. Remember, second minus first, and 0, take 2, neg 3, take 3, to get this. Okay, so now the most convenient way, as we've said before, to find a missing point is let the point equal these parametric equations. So that's important. Okay, those parametric equations. So if it's on the line, then these are good descriptions of the x, y, and z. Now that's going to meet the plane when what? When the x, y, and z satisfy the equation. Okay, so you put the parametric equations of any point on the line into the plane equation, and when you do that and solve, you get t. And once you specify t, you lock down the point. Specify t implies you specify a single point, a unique point on the line, which is that multiple of the direction vector from the fixed point, if you remember that parameter t. Actually trying to remember what t is describing about that system. Remember, a parameter reflects a different property of the system. Okay, so therefore when t is -2, substitute t is -2 back into this line here and get a point. Remember, when you have a set of parametric equations specifying a particular t, specifies a unique point on that line. All right, so that's our trick here. So please remember this trick when working with lines and planes and trying to find points of intersection. A point on a plane is best in general described by its x, y, and z in parametric form. A handy use of that parametric form. Right, your turn. Okay, so here we go, and we've got 6 and 7 here. Okay, and give you the hint, find the parametric equations, and then use that as your general point and sub it in. All right, so, and question 7 is a bit of a revision of parametric equations versus Cartesian and all that. Okay, have a go, and I'll show you the solutions now. Okay, so here's 6 and part of 7. Okay, and let's have a look at the rest of 7. All right, so there's 7. Hope you're going well. Keep it simple in your thoughts there. Let's go on now. And just another example of what we can do with our plane. The coordinates of the foot of the normal to the plane, there, we've got to find the foot of the normal and hence find the shortest distance. So that'll be the length of that vector, won't it? Because if we're doing the shortest distance, that's the perpendicular, and that's the foot of the normal. Okay, so let's draw the diagram. So we've got this point, we've got a plane. So now, this plane has a normal vector 1, -1, 2. Why? Because the normal ends up, the components of the normal end up as the coefficients of the x, y, and z in the equation. So the parametric equations of AN, we don't know what the foot of that is. Okay, so what we're going to say is, if it's got this normal vector 1, -1, 2, can we make up parametric equations? Oh, well, they've skipped a bit of a step here, because here you're saying if you have this vector coming down here, it's 2 plus 1 lot of t, -1, right, take 1t, going straight to the parametric equations, 3 plus 2t, because you're generating the parametric equations directly rather than saying what? X, Y, Z equals 2 -1, 3 plus t by 1 -1, 2, because you're on the normal vector coming into that plane. You want the normal vector because you want the foot of the perpendicular, and then expanding that. Okay, so we're leaving out that step. So just think of that, make sure you're clear, and that line is perpendicular to the plane because we want the foot of the normal and then the shortest distance. So we need the perpendicular coming down there. And where does this point here meet the plane? Well, we're going to use that point and sub it in place of x, y, and z in here. So we get the t value on that line, which is going to land at the point of intersection there, the n. And so t is 3, and subbing it back into the parametric equations up here, you get 5 neg 4, 9. So I've left out a couple of little steps there. So what's the shortest distance? It'll be the length of AN. So AN, find AN, which is 5 take 2, neg 4 take neg 1, so it's going from there to A and getting the length of that. So it's the shortest distance because we're working with the perpendicular distance and finding the foot of that normal. So lots of little tricks. Start thinking about the tricks, and one of the most important things is if you're trying to find a missing point there, let the point have the parametric as coordinates, let the point's coordinates have the x, y and z from the parametric equations. All right, come down and it's your turn and have a go. Just a few little ones here. Okay, and I think it's important to do most of these and to think about why they're working, because that's the trick in this subject. We've got the routine questions, then sometimes we'll ask you to put some stuff together for yourself. Okay, pause that and have a go. I've got some more for you though. Okay, and this one I remember now looking at this, that is incorrect. It should be take D there. Okay, so just note that. That should be take D. Okay, so there's some more. I'll just bring up the last little bit now. There. Okay. All right, so have a go, and I'm going to show you the solutions now. Okay, so there's 8, A and B. Got quite a few solutions for you here. Oops, just bring C up. And C then. And 9. 9 and 10. I think we've got most to 11 on. We'll have a look at that in a minute. There's 11, A and B. And then C. And then 12. Quite a bit of practice here, it's important to do it. And 13. And this big question 14 is the important one. Okay. And then down to there. 15. And down to 17. And there's the last of those then. Okay. So how are you going? Go back and check the thinking there. The ship's getting a bit rocky here. This one's slipping off the side. Let's go on now and let's have a look. The angle between a line and a plane. So you might have guessed we're going to try and do some of this stuff. We're investigating all the geometry things with vectors. So here's a line, call it L, and here's the plane and there's its normal. You can see why the normal is very, very important now in defining the direction of the plane. Okay, so the angle that we want is this angle down here. And so we can say, to get that angle though, that's hard. We can get the angle between the line that's given and the normal to the plane more easily. So we could say here, the sine of this one, because these are in the same right angle triangle, is the cos of this one. And we can get the cos of that one more easily. What is the cos of the angle between two vectors? You might remember n dot L is equal to length of n, length of L, cos theta. So if we want the angle between them, we'll divide by it. So here's our result over here. Cos of theta is easier to get because theta is the angle between two vectors, and that's defined easily so with a dot product. And that's the cos of theta, so phi has the same sign as that, so it's sine neg 1 of this. Neat little trick, isn't it? Can you start to see that trick? If you're trying to find an angle, the dot product is the best, and maybe you relate another complementary angle via change it to sine of that one. It's the cos of the angle between the two. All right, remember the cos of 60 is the sine of 30. The cos of 40 is the sine of 50. All that stuff. Okay, come down now and have a look at an example. This is what I want you to do in a minute. So we have a plane and we have a line with parametric equations. So the normal here is the coefficients here, 1, 2 and -1. And the line has these, remember, direction numbers. 1, -1, the coefficient of t is the direction vector of the line. So now we can go straight to it, the angle between it, sine -1 of the size of the dot product over the length there, because we're looking at the acute angle between them. We don't know the directions of n and l, so we'll just use the size here of the dot product and produce the acute angle. And then we can do that on the calculator. Okay, and leave it in this exact form. And in the Casio, if you've got it in math mode for run, then you'll get 30 degrees exactly. Notice that we'd use degrees, not radians here, because we're talking about angles between lines and in space here. All right, are you ready? Have a go at these couple. We've got 3 here, A, B and C. So just remember to revise your equation of a line in space there. You've got to be able to do it with the vector statement, parametric or Cartesian. All right, come down now and have a look at the solutions. Oh, the ship's rocking again, going off to the side there. Okay, let's do the last little bit now. How are you going? I hope you're getting the hang of it. And angle between 2 planes. So here we have one plane and there's another plane, and we're going to obviously try to relate the angle between the planes coming along here, viewing it that way, the angle between the planes as, oops, I've done the wrong thing there. Here we got the angle between the planes as related to the angle between the normals. So let's have a look. I just drew that in. Here are the normals to the planes, and they are the easiest way of defining a flat surface, by the normals. And so if we do a bit of geometry, these are perpendicular. If that's theta, sum of angles on a straight line, that's 180 take theta. So this one over here is theta. Hey, that's a bonus, because that's the angle between 2 vectors. And we know the easy way of getting the angle between 2 vectors. Here it is over here. The side, the acute angle, size of the dot product divided by the length of the 2 vectors there. Okay, and the cosine of the acute angle. We're just going to put this as the size of that, or modulus of it, and that's going to give us a positive. So that's going to give us the acute angle. And we won't be doing that one. We're going to do this one in here, in other words. Okay, so that's easy as well. So between the 2 planes, the angle between the 2 planes is the same as the angle between the 2 normals, which is therefore just cos -1. You don't have to change it to sine. So keep your wits about you as to what's going on here. The geometry is relatively simple. Okay, let's have a look at some problems for you and then we'll finish up. So here we have an acute angle between these 2 planes. First job, maybe get a little picture. But the first one has a normal, which is the coefficients of x, y and z. And the second one has coefficients of x, y and z. And so they define the 2 normals. And if you want the acute angle, it's cos -1 of the size of the dot product over the 2 lengths. Just remembering where that came from. The dot product n1, n2 is length of n1 by length of n2 by the cos of the angle. And just rearranging that, and then we're going to put this modulus here because we're looking at the acute angle. Okay, so then we work out our numbers and come to -2 for the dot product, so that becomes 2, and then we state it there. usually we would write this answer to 3 significant figures. This is 2 decimal places. We'd usually say approximately, or that sign, 72.0 to 3 significant figures up there. Okay, so let's have a look at doing some problems now. Find the acute angle between the planes of those equations. So that's just a straight exercise. See what you think. And I'll show you the solutions. Okay, so there we have the answers to those. And that's all for this one. And I think there's just one more presentation talking about intersections of planes and overlapping with 3x3 systems. Okay, so that's it for me now. I'll catch you in that final presentation. Cheers.